In this video, we're looking at differentiating to integrate. It's a bit of a weird concept, but basically you can discover integrals, essentially. So last video, we sort of discussed what an integral was for the very first time. And we sort of, if f dash of x was 2x, what is that original function going to be? And we thought about it for a little while, and we thought maybe that original function was x squared, because the derivative of x squared is 2x. And in fact, it could have been x squared plus any constant when we thought about it a bit more. So that was an example of discovering an integral. You sort of thought about what it could be, and then you checked. Now, whenever you get these questions in a test or exam, the questions go like this. Part A, do a derivative. Part B, do an integral. So we'll see how this works. So f of x is e to the x squared. So that's going to be let. Then f dash of x, we've got to use the chain rule. So you get e to the x squared times the baby, which is 2x. Baby is the derivative of the stuff up there. Derivative of x squared is 2x. So the derivative there is 2x e to the x squared. There we go. Okay, hence find the derivative of x e to the x squared. Okay, so we know something from part A. So we know that if I take e to the x squared and I differentiate it, in part A I showed that I get 2x e to the x squared. So in theory, if I integrate 2x e to the x squared, I should get e to the x squared. So from A, we've got that the integral of 2x e to the x squared is e to the x squared. Now, there's a couple of things you can do with integrals. So if you look at the integral of f plus g, well, I guess this is like f of x plus g of x. That will be the same as both the integrals added together. So you can do integrals piece by piece. We have actually been using this one quite a bit. We just don't really explicitly say when we're using it because it feels intuitive to do it. The other one we use quite a bit as well. K times a function is k times the whole integral. These rules also work for derivatives. So we're going to use these two. Basically what's going to happen is the 2 there is going to come out the front. So we're going to go that 2 times the integral of x e to the x squared is e to the x squared. And now we can just divide both sides by 2. By the way, this should have a plus c on the end already. Or maybe I'll just do it at the very end, just to make it a bit nicer. So that tells us that the integral of x e to the x squared is e to the x squared over 2 plus c. Done. Now, if we want, we can actually just check that this is correct. So let's do that over here. So if we let a function like, I don't know, y equal e to the x squared over 2, the y dx should equal, now we know what the derivative of the stuff on top is because we've just done it in part A. So you get that, and it's over 2 on the bottom. So you just get x e to the x squared. So we have actually found the answer here. Now, c's got to be a real number. And technically back here, we should have also had a different constant. So I usually call this one up here C1. And then this is now plus c there. Now, C1 and C are technically different things because this whole thing was plus c all over 2. But since it can just be any constant, c is just c1 over 2. And we can just call it like a new letter and then move on like that. The constant makes it a bit confusing, but I hope the premise of the argument makes a bit of sense. Differentiate x log of x, so f of x is x log of x. To differentiate something like this, we need the product rule. So u dash has got to be 1 and b dash is 1 over x. So f dash of x is u dash v plus uv dash, which is 1 log of x plus x times 1 over x. So that's f dash of x there. And we can simplify this down a little bit because the first term is just log of x and the second term is 1. So there's our derivative. So what have we learnt from this part? We've learnt that if I take x log of x as a starting point and I differentiate that, I get log of x plus 1. That's what I've learnt. So then if I integrate that, I should get back to what I started with. Hence, find the integral of log. So with these part B's, you always start with this statement that we just learnt. So I've learnt that if I take log of x plus 1, and I do the integral to that, I should get x log of x. Now, I'm not going to worry about doing the plus c. I don't think that's going to make it a bit more confusing. So I'll put it in at the end. Let's split up this integral into two pieces. So we can go, this is the integral of log of x plus the integral of 1 should equal x log of x. And we actually know what the integral of 1 is. That thing's just x. And that is still just the integral of log of x. There. Now, I want to get the integral of log of x equals something. So what I want to do is now take x from both sides. So we get that the integral of log of x is x log of x. Take x. Cool. All right, now we better fix up our plus c's. Plus c1. C1 is in R. This is still plus the same constant c1, that hasn't changed. Now, technically, when we did the integral of 1, over here, you've got still that plus c1. You actually get another constant of integration. We'll call it c2. But you can sort of imagine moving c2 over here as well. And then it all just bundles into the same one big constant. So I'm just going to now call this constant c. It's different to c1, but c is a real number as well. Try not to get too hung up on the constant stuff. The point is actually getting the integral here. Now, let's check our answer. Because if y was x log of x, take x, I'm really hoping that when I do the derivative of that stuff, I get the log of x. That's what I was hoping for. So we got to use the product rule on that first bit. I know we did this before, but we'll just do it again for completeness. V is log of x. V dash is 1 over x, and u dash is 1. So that first bit is going to become 1 log of x plus x times 1 over x. Take. So that was all the first bit there. And then the second bit is just 1. So this becomes log of x plus 1, take 1. Hey, it's log of x. So, hey, we just checked it. It did work. When I did the derivative of that thing, I do get log of x.